All right, now we are going to look at a different problem on how we can compute the statistical significance of results. In this example, this is a graph problem. We are given a graph with weighted edges, and we want to find densely, not strongly connected, because strongly connected has a different meaning. Strongly connected means that there's a path between all pairs of nodes. Find such a subgraph so that there's a path between all pairs of nodes in a directed graph. So our graph is not directed. We are given an undirected, but the edges are weighted with some weights. And our goal is to find a subgraph here, or a number of subgraphs here, which are densely connected clusters of nodes. So imagine, for example, this may be the weights, by the way, may be all one. You may also be given an unweighted graph. So you're given the friendship graph of our students in Otto, for example, whether they are friends or not. And your goal is to find out clusters of students who are all friends with each other. In that cluster, everybody is friends with. Not everybody. We are not saying it should be a clique, but it should be as close as possible to a clique. Okay, so our goal is to have an algorithm to do that. And imagine we have an algorithm, and it spits out saying that, okay, this subgraph in this graph is densely connected. These are the densely connected subgraphs that I have found. Then we're going to ask and another algorithm gives a different result. Which one produces a better result? How to compare the clusters? For example, you can, given a cluster of nodes, given a subgraph, we can actually compute its density as a ratio of the number of edges that exist in that subgraph over all possible number of edges that could have existed. It's like if it was a clique or if it was a complete graph. And imagine one algorithm produces a cluster which says, I have found a cluster of students of 10 students and they all know each other. All right? I mean, all the edges between them exist. It means it must be a good result, right? Another algorithm tells you that I have found a group of 20 students, but there are some missing edges. And not all 20 of them know each other, but only a couple of missing edges. Which one is the better answer? So there are two measures that are in conflict with each other. Like as the size of the cluster gets larger, if you try to find more larger group of students, you're likely to miss some of the edges. It may be more difficult to find a clique, a complete graph. But on the other hand, as the number of students get smaller, you may find clusters that are very dense. So density and the number of students are two measures that you cannot satisfy at the same time. For example, imagine an algorithm also reports another result. I have found 3 students and they all know each other. It's a full graph, it's a clique. So isn't my algorithm good? So here, the question that we should ask ourselves in both cases, in both algorithms, is that how different are these results from random? Because imagine a university in which all the students are already friends with each other. In that case, if you just select a random cluster, a random group of students from this university, I found 30 students and they all know each other. Of course they will know each other because all the students already know each other in this university. So if you have a random algorithm, if you just pick random 30 students, it will be a full graph. It will be a complete graph here. So in this case, the density of the original graph is also important, right? Maybe this problem may be more difficult problem if you're given a lot of students in a university where the friendship graph is actually a sparse graph. Most of the connections are missing. in such a sparse graph, finding these densely dense subgraphs may be a challenging problem. All right, so this is the problem we are facing. And here the statistical significance computation is used to compare these two different algorithms. One algorithm gives some result. We need to uh, assign some kind of fitness, some kind of how good this result is. And the statement that I just made is how different this result from a randomly selected group of same size students is going to be our fitness, or how good that result is. This is what it's going to show, and that's what the statistical significance is. Here, our raw scores are going to be the total number of total weights in the subgraph that we identify. If we actually the sum of the weights on the minimum spanning tree of that graph. This is one decision that how you compute your raw scores really depends on the algorithm and other things. But here in this example, I think we computed the minimum spanning tree of these subgraphs, and the total edge weights in that minimum spanning tree was the raw score in that graph. And in order to compute the statistical, here's again the same sentence. This is what we need to find out. If we found a cluster of size n and students, how different, how its density, how different its how different it is from a random cluster of same size. Because we need to, when we're computing this statistical significance, obviously the number of students we found in that subgraph is important, right? I mean, if you find a cluster of 4 students, it may be more likely to be dense if you just randomly selected 4 students from the graph. But if you increase this number, if you select 50 students from that graph, the probability that it's still going to be dense may be very low, depending on your original graph's density, of course. But obviously, the size of that cluster is important. Now, here is how we can, the idea is the same. Our first goal will be to build up the null distribution that will serve us as the background distribution in our hypothesis testing. Our row score here is the weight of the minimum spanning tree of a particular cluster. So what we do here is that we select random subsets of 20. So just given a graph, it's really easy to write some code to just select random 20 nodes from that graph. And for those random 20 nodes, compute the minimum spanning tree in that subgraph induced by those 20 nodes. And just take a look at the sum of the spanning tree weights. And if we see that, for example, for a cluster of size 20 in this particular graph that we used, we see that we have the distribution of those tree weights look like this. Okay, so this looks like a family of distributions, right? Which family is this? If we have a distribution that is like this, we don't have any negative values here in this case because it's the sum of weights of edges. And this is the histogram. What you see here is the histogram of raw scores when we select those 20 nodes randomly from the graph. It says that some of them, very few of them, has minimum spanning tree weights around 10 and 15. Okay, so this is, by the way, I need to also show what these axes mean. Okay, x-axis is this raw score. X-axis is the raw score that we compute. So here, there are some random subgraphs of size 20 with minimum spanning tree edge weights between 10 and 15, if you look at this point here. And there are many. So this is like we sampled around, I think, 500,000 from that random universe. We sampled 500 random samples of size 20. And out of those 500,000, 400,000 contains 0 row scores. A lot of them have 0, and the histogram shows very few of them get large scores. Maybe only one get 38. Okay, so if you get a score of 38, probably since if it seems like it's very close to this 0 on the y-axis, because if you look at the scale of this graph, it's from between 0 and 500,000. So if you have something 1, it would just be close to 0 here. Maybe one cluster out of those 500,000 contained a score of 38, large score, but many of them contain this. So if you look at this histogram, it looks like the exponential distribution, the family of exponential distribution family. And what we can do is, we can actually, this looks like an exponential decay. The probability density function of the exponential distribution is this. By using packages like MATLAB, we can actually fit, or by playing with different values of this lambda. The only parameter in exponential distribution is lambda. And it basically tells the speed of decay. So for larger values of lambda, the decay is faster. For smaller values of lambda, for example, when lambda is 0.5, the decay is slower. Okay, it tells. So by looking at the histogram we have found, we can change the value of lambda for our histogram to try to fit an exponential distribution on it. And this is what we did actually. We have generated clusters of different sizes. For example, for a cluster of size 30, the decay was slower compared to a cluster of size 5. So we get different cluster sizes, constructed the histograms, fitted exponential distributions on these histograms, and found different lambdas specific for them. And after we fit an exponential distribution, it's really easy to compute the statistical significance as a p-value. P-value is the probability. It's the probability that a random score is going to be larger than the row score you obtained. So W here, imagine your algorithm. One of the algorithms produced a cluster, and if you do this, compute the same row score, the minimum sparing 3 weight for that subgraph, you, by the way, am I recording? Yeah. You get a value of W. So what is the probability to obtain the score of W or larger randomly from this distribution of random clusters? That probability can be computed as the area under the curve. So if you take the integral from W to infinity, okay, so from W to infinity, what is the total area under the curve from W to infinity is this probability, because the area under the curve of a probability density function of this continuous random variable gives me the probability. And the good thing about the exponential distribution is that its cumulative distribution function is actually one. This is 1 minus the cumulative distribution. Is simpler than its probability density function. So if you take the integral turns out to be this, which allows you to compute statistical significance for your row score. So our row score is W here. By plugging it into this equation, again, we have lambdas, just like Cardinal-Statistical statistics. These lambdas this time are the parameters for the exponential distribution. And we compute this just like they computed these lambdas for different Pan-Blossom matrices. We have different lambdas for clusters of different sizes. For specific n, we have a lambda. And this allows you to compare like this. For example, lambda 5 was 1.7, lambda 20 was 0.36 in our specific example, in our specific graph. And when we find the cluster, an algorithm finds a cluster of size 5 with minimum spanning 3 edge weights summing with the row score 15. And we find another cluster of size 20 and the row score is 45. Okay, so it seems like the second result is better, right? It says both larger, a cluster of size 20, more nodes, a subgraph of a larger cluster of more nodes in it, 20 nodes, and with edge weights 45. The total edge weights is also like 3 times this. the total edge weights is 3 times the previous score. So it seems like the second answer is a better answer, a better result of the algorithm. But if you do the statistical significance computation, actually finding a subgraph of size 5 with edges summing up to 15, minimum spanning tree edge weight summing up to 15, has a lower p-value, which means that this is more different from a random score. So this is a more valuable, more statistically significant result compared to the second one, compared to the latter, which contains 20 nodes and 45. All right. So this is just showing how we can use the some null distribution or to compute statistical significance for different problems. All right, so this is, I'm going to conclude this chapter now and going to jump to a new topic. All right, any questions before I start suffix trees? Okay, so let's start our problem now, a new problem. It's this. The suffix tree, as I said, it's an index structure that we are going to learn. It's a data structure which allows different types of queries, maybe approximate matching. But in this, we are going to see just the basic version of suffix trees with construction times that are not linear. We are going to see it's going to take more time. So I think we are going to have an n square construction time algorithm, which is a lot actually when you're building an index structure. If you have a quadratic index building time, it will be very slow. But just know that there are suffix trees are studied a lot in literature, and there are algorithms to construct suffix trees in linear time and using linear storage. So there are really efficient data structures. So what's the problem that we're trying to solve here? We're trying to solve this problem. We have a very long string, let's call it string S, and we have a small pattern, a small string, let's call P. And in this basic version of the problem, our goal is to figure out whether P occurs in its entirety in S. Okay, so it's like similar to sequence alignment where we have no end gap penalties, but when we were to do this sequence alignment, we would have to spend a lot of space and time, quadratic space, quadratic time, and if you're looking for the simpler version in which we're not looking for an alignment with some mismatches and gaps, we're just looking for whether P occurs exactly in S. Okay. For that, we don't need to actually do any alignment. We can just scan our string we can have a window of length P, whatever the length of P is. We can have this window, and we can slide this window one by one, and trying to match the characters of S to P. So this is linear scan, and it's going to take time proportional to the length of S. Okay, so this I'm using this as the length of S. So because you will have to scan starting from S all the way to the end. Now we are going to see an algorithm which will be used to find the same answer to this query, to find where P occurs in S in this much of time, in all P time. Okay, regardless, so this is really something interesting in terms of a result, because regardless of the size of the database, size of string S, if you look at this computational complexity, the string size S here it's not there. All right, so you may have a very large database and you can double the database size. You will still be able to search for patterns in this database in time proportional to the length of your pattern, not the length of your database. If your pattern is short, this will indicate very fast pattern search times in your database. And we are going to see one way to do that is to use a data structure named suffix tree. Okay, and it can be, the suffix trees can be used for different purposes as well. There's a generalization. So this is the simplest original problem. For example, by building a suffix tree for two large strings, S1 and S2, we can find their longest common substrings. Or we can find, for example, we can build suffix trees for many long strings. And after that, we can find, for example, small strings that are unique to them. So that's an interesting problem, right? I mean, it seems a different problem than this pattern search. Imagine we have a problem like this. We are given 1,000 strings like this, and your goal is to find small strings which are unique to those. So why do you need? What is the biological motivation behind this? Maybe you may be trying to design maybe primers, or you may be trying to design a chip in which you cannot put the entire sequence onto those chip because these are long, but these are like signature sequences. If there's a short sequence which only occurs in S1 and not in S2, S3, or S4, this short sequence may act like a signature sequence, which these short sequences, they are sometimes called oligonucleotides. So this finding signature oligonucleotides for a set of sequences like this is possible with the utilization of suffix trees. So that's a different problem. Now let's focus on this classical problem of suffix trees. In simplest version, we are looking for exact matches, and there are extensions, variations of suffix trees which we can search approximately. P can also be searched approximately in S, so we can also have these in the newer version of suffix trees. But in this introductory course, I'm going to just show you the simplest version. We will see the simplest construction algorithm, but we have built enough mystery now. What are these suffix trees? You may be wondering. I have been mentioning how we can use them, how fast they will do, but what's a suffix tree? As the name suggests, given a string S, a suffix of a string S. So if we have the string S, which is composed of characters from 1 to n, okay, if any substring of this S, if this lowercase s indicates a substring, we can indicate the substrings with two indices, right? Okay, Sij. Let Sij indicate a substring of this S string S from the ith character all the way to the jth character. Okay, so if I have characters from S1 to Sn, any substring of the string S can be indicated by two indices, the start index and end index, then that will be a substring. All substrings in which go all the way to n. Okay, so these are all these substrings that I indicate here. They are called suffixes. A suffix is a substring which starts at some character here and goes all the way to the end. Okay, so that's the definition of suffix. And similarly, we also have prefixes. Okay, what's a prefix? Prefix will be a substring starting from 1 and going to some index I. Okay, so prefix will be this. Now, a suffix tree is a given for a string S. A suffix tree is a tree of all the possible suffixes of S. Given S, how many suffixes a string S can have? Okay, given a string S of length n, how many suffixes do we have? So I'm going to build a tree of those, and each suffix is going to be indicated by a leaf node. Okay, so we are going to have leaf nodes on our tree, and each leaf node will indicate a suffix, and the answer is correct from Ramazan. It's the number of leaf nodes I'm going to have is n, right? Because all the possible ways we can have. So the last character is a suffix. The last two characters are it's a suffix. The last three characters is a suffix. The string n, it's the string s itself, going all the way to the first character, is also a suffix. All right, the string s itself, because our definition of suffixes, the only restriction is it has to end at n. Now, in our tree, in our suffix tree, we will have these restrictions. First of all the suffixes are going to be represented as leaf nodes. And in this tree, the edges are going to be substrings of s. In other words, on the edges here. So the edges are going to have some labels from some between I and j. They are not necessarily suffixes, but they are substrings. Okay. Now, what will happen is that what makes a tree is that there is a unique path from the root node to any leaf node. This is what's one property of trees. So if you concatenate the edge labels, let's call it, for example, edge label 1, edge label 2, and imagine we have arrived at this suffix with 3 edges, okay? There may be 2 intermediate nodes. So if this is the suffix sin, concatenating E1, E2, and E3 will give me that suffix in. Okay, so that's one thing. So we will have 3 different paths like this. So now you see what's going on here. I'm going to have different edge labels here. Now, what can you say about this suffix here and this suffix here? Let's call this another suffix. So if you look at this is our root node. If you look at the path from the root node to these suffixes, for example, this one is E4, E5. If you look at this suffix S here, it's a concatenation of E1, E4, E5. E1 plus E4 plus E5, where plus indicates concatenation of strings, right? One after another. It indicates here another suffix. So these two suffixes share a prefix E1, right? Now, we are going to build this suffix tree in such a way that any 2 outgoing edges from any intermediate node, the edge labels will always start with different characters. That's going to be one restriction. For example, if this E1 starts with the letter A, okay, if E1 starts with the letter A, no other edge label is going to start with A. That's going to be one restriction, because what we want to ensure is that by looking at outgoing edges from some intermediate node, and when we have some suffix that we are looking for example, what we want to do is we need to uniquely follow a path by looking at characters one by one. In order to have a unique path to follow a specific suffix, the edge labels are going to be organized in such a way that no 2 edge labels going out of an intermediate node will start with the same character. They may have additional characters coming afterwards, but they will not start with the same character. Okay, we are going to arrange it like that when we are building our tree. Now, these are some basic properties of suffix trees. Now, let's take a look at this problem. Imagine I have a pattern P that occurs in the middle of my string S. Okay? Do you see something about this P? If a pattern P occurs in a string, what does it need to be? It has to be a prefix of a suffix, right? Any pattern. So if we have all of the suffixes, just look at any pattern that occurs anywhere in the string. If the suffix tree represents all of the suffixes, this pattern P has to be a prefix of some suffix if that pattern exists. If it's the prefix of suffix, what does that mean? It should be traceable. There should be a path starting from the root node. And if that suffix is represented nicely in the suffix tree, we should be able to read out the letters of pattern P starting from the root node by following the path. And as soon as we match all of the characters of pattern P on somewhere on this root node, we don't need to go all the way to the end of the leaf node. We can just stop whenever we have found out all the letters of pattern P here on the path from the root node. We can stop at that point and say, okay, our pattern exists in this string. And for example, imagine the search for pattern P ends at the middle of an edge label while we are tracing the characters of pattern P. Imagine we have ended here. What does that mean? For example, can you tell me in how many different places, for example, how many times pattern P occurs in this string? Can you tell me by looking at this tree, what is the number of times pattern P occurs in this tree? What do I need to look at? So for example, how many suffixes are below this point? So it's the number of leaf nodes in this subtree, right? The number of leaf nodes in this subtree are there different suffixes. One of them is one suffix, the other is another suffix. It means that prefix P was the pattern P was a prefix of two different suffixes, which are two different nodes in this tree, but they shared some initial path from the root node. So the size of the subtree, not the entire size actually, the number of leaf nodes in the subtree where my pattern ended tells me how many times this pattern P occurs in this tree. So as you can see, the number of steps that I took, if you have this number of leaf nodes stored in intermediate nodes, when you're building the tree, it's really easy to also store the number of leaf nodes that are rooted in that are in this subtree easily. So if you have this additional information in every subtree, the number of times the pattern P occurs in this, we do not know the length of the substrings. The query, you mean the pattern P? Which substring are you referring to? Oh, you mean the suffixes? The length of Sij is just j minus a plus 1, right? Length of a substring. When you have a substring like this, its length is always j minus I plus 1. It will contain. No, we don't know I and j. Yeah, when we don't know I and j, and it can be anything. But here, in this case, this Sij will not be. When we are solving this problem of searching for a pattern, we have the pattern that is given, and pattern will be a substring. So we will know these things. So these substrings, the edge labels will be there. So this Sij is just any substring that I mentioned when I was discussing the terminology. We will not have any arbitrary substring in this tree. Okay, so let's try to build a suffix tree, for example, for some string. Let's try to do that. For example, let's try to build a suffix tree for ACG, A, C, T, G, A, C, A. Okay, let me see. Let me end this with T. Okay. Okay. Now, look at this. Nucleotide sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now I'm going to show you in the last 15 minutes how we can build this suffix tree, and in that way I'm going to describe you the algorithm to build the suffix tree. So we'll build the suffix tree starting with the entire, the algorithm that we are going to describe is very simple. It's iterative. It inserts all the suffixes one by one to the tree, starting with the suffix that contains the entire character. So we will start building our suffix tree like this. This is suffix number 1. So we can indicate every suffix by a single index, right? I. Which indicates where it starts, because all of the suffixes end at and. So we can just use a single index to indicate suffixes. So suffix number 1 refers to the entire sequence. Suffix number 2 refers to the string that starts at C. Okay. Suffix number 3 is the string that starts at G. And suffix number 11, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So suffix number 11 is this single T at the end. Now, we are going to build a suffix tree by inserting suffixes from S1 to S11 one by one iteratively. So it's going to be like this. This is my root node. I start building my suffix tree, and I will have a single leaf node, this one, and here I'm going to, my edge label is going to be from S1 to S11. The edge labels can be substrings, so they can be SIJs, but as you see, when I'm building the tree, I indicate what that edge label is. It's S1 to S11. So if we had a single suffix in our tree, where this is the root node, let's label it as R, the root node, you see this is the tree looks like this. Now I'm going to insert the second suffix, CGA, and it's going to, and let me also introduce a third suffix too, and the tree is going to look very boring like this. 11, not 11. Why did I say 11 here? It's S1. I wanted to write S1 to indicate suffix 1. Okay, or just simply 1. Okay, so actually let's call this root node either suffix 1. So this is the leaf node for suffix 1. I wanted to write just 1 actually, there it doesn't matter. So this is S111. This is my first suffix. When I enter the second suffix and the third suffix, the suffix tree looks like this. S311, S211. Okay, right now this is a valid suffix tree because all of the edges start with a different character. This edge starts with A, this edge starts with C, this edge starts with G. So the suffix tree looks like this. Now let's insert the fourth suffix, which is, now when we are inserting ACT, GAC, and AT, can I have it as a separate string like this, S411, and put the fourth suffix? Is this correct? No. Why? Because this edge and this edge, they both start with the letter A. Okay, so this is the problem. When this one starts, if you look at S411, which is this ACT itself, it starts with A. This edge also starts with A. I cannot have two edges starting with the same letter. That's one of the constraints in suffix tree. So the last thing that I drove here is not correct. So what do I need to do? When I'm inserting, so here's what we're doing when we are inserting. When we are inserting a new suffix, we try to match its characters one by one from the root node. If from the root node we cannot have a match, we just have it as like in this case of the suffix 2 and suffix 3, there was only one edge. I mean, in the case of suffix 2, there was only one edge coming out of root node, which started with an A, and suffix 2 started with a C, so we could not follow this edge for suffix 2. And at this point, we inserted a new edge label and attached R suffix to that. Now, in this case, where we are trying to match the characters of the fourth suffix, we are able to do that because this edge starts with the letter A. So what happens is that, but the second character also matches, right? The second character, C, also matches. But if you look at the third characters, the third character of this first suffix is G, while the third character of this fourth suffix is T. Then there's a mismatch. So I cannot use the edge label. The edge label here is like going like ACG, but the suffix that I'm trying to insert is ACT. So what do? We divide this edge into two and do it like this. This is my root node. The AC part is shared. I put an intermediate node here. The part of the edge that says GAC TGA CAT. This one, which is actually the string S411. So this is the substring S, not 4, 3, 1, 2, 3. S311, this substring is here, and this is S12. As you can see, S12, another SIJ, and this is another SIJ, but we know what they are because while we're building this. So this is for AC concatenated with GCA, this gives me the first suffix. And AC concatenated with this time, this is something different. We had a mismatch at G and T, therefore the edge labels, they start with different things. So this one is TGA CAT, and this is for the fourth suffix. And the second and third suffixes are still there nicely, starting with a C here and starting with a G here. Okay, so this is how we inserted the fourth character, a fourth suffix. Now the fifth suffix is CTA. So in order to insert this one, again, we are going to do the same thing. Now we are going to match the first character here. And for that, since there was a mismatch at the second letter, so this one goes with CG and this is like CT, we are going to just chop the edge at this point at the C and insert an intermediate node. The edge that goes to suffix 2 is going to continue with GA whatever, and this one, the fifth suffix, is going to continue with CT. Okay, so we just go ahead and try to match the characters of our suffix one by one, and at the time of a first mismatch, we're going to insert a new intermediate node there, and the mismatch part, the mismatch characters are going to be put into the edge label, TGACAT, like this, and we are going to insert the fifth suffix. Now, when we come to this TGA, 1, 2, 3, 4, 5, 6 suffix, 6 suffix is going to be directly inserted here because there is no, so this edge starts with A, this edge starts with C, this edge starts with G. There is no edge that starts with T. So this one, the sixth suffix is also going to go out directly from the root node, which will start with T, TGACAT. Now, when we start to insert GACAT, there will be a match in this GAC node. We will be matching this GAC part, add an intermediate node, and the mismatching part, which is AT, is going to come here, which will be our seventh suffix. Now, the branching factor of this suffix tree, as you can see, is the size of the alphabet, because the number of outgoing nodes from an intermediate node at most can be the number of letters in your alphabet. We cannot have, can this root node have another child? It now has 4 children, 4 outgoing edges. Can we have another branch coming out of root R? No, it's not possible because this one starts with T, this one starts with A, this one C, and this one G. These are all the letters that are possible. If there's another thing that is coming out here, it will by pigeonhole principle, it will match one of these characters I already have. So we cannot have that. All right. So the construction algorithm is this easy. And when you come to, for example, AT, there is one starting with A, and AC, we are going to introduce another intermediate node in the middle here. AC is going to be one part, there will be the last suffix, the 11th suffix is going to share the A part, and T is going to be here. This A is going to be deleted. It will be the label of this edge right here. Okay, so it's going to be AC. It's still going to read. The previous suffixes will not be affected by this, and we are trying to match all the characters one by one, and at the first mismatch, we add a new edge and insert our suffix here. Now, this is the original algorithm. Before I stop today, now I will going to tell you something, ask you something. All the suffixes has to be, they have to be represented as leaf nodes, right? This is also one of the properties of suffix trees. Now, do all strings have proper suffix trees? So in other words, can you tell me a string in which I selected this string in such a way that this never happens? I selected this string as the case where it is possible to draw a suffix tree properly for it. But are there strings in which suffix trees are not possible to draw? I mean, for example, what if this didn't end with a T? I put this T on purpose. If it ended with an A, that would be a problem for me. Can you think of the reason why ending with A would be a problem? For example, when you look at this tree, AT, I was able to edit as a leaf node. What if it was just an A? What would happen there? It's not the palindromes, actually. No, it's not the palindromes that are, because we are not, in palindromes, the reverse reading of the string is also the same. You're not doing anything reverse. It's not the palindromes that are problematic. It's the suffixes that are prefixes of other suffix. So it's like a riddle, but look at this. Look at this A. If we were to add this last A as a suffix to this tree, what would happen? A is the letter here. I have an AC here, and A just ended at this intermediate node. Okay, there is an A, so it's going to let me draw it someplace else. So it's going to, because it's really small, crowded there. So I have AC something here going this way. And now let's try to insert the suffix A to this tree. Okay, it starts with an A. What should I do? I should just I should do something like this. It's the part of A is going to be shared, and this other one continues with C like this and goes on like this. So this AC part should be chopped because my suffix is just A. It doesn't contain a C afterwards. So this will be a separate part for the previous suffix, and there should be a leaf node for this new suffix A. All right, so for this new suffix A. But what about here? It's not there was a constraint that all the edge labels have to be substring of string S. So we either need to put the leaf node here for that suffix saying that, okay, there may be some edge labels with empty strings, okay? Because in order to represent this suffix A is a concatenation of these two edge labels. This is that single suffix A, all right? The last suffix number, this time it's 10 when you erase that T at the end. So for suffix 10, it's just A. The edge label should be empty because the reason was the suffix actually ended. The suffix ended at an intermediate node like this. It didn't go all the way to a leaf node. It ended here in that intermediate node. This is not a leaf node. You cannot make, for example, if you don't put this here, if you just leave it like this here, as you can see, our suffix A ended at an intermediate node. Why? Because that suffix was a prefix. It was a prefix of another suffix. A here is a prefix of this suffix. A is prefix of this suffix. Okay? But when I put T here, that T was served a purpose. the pattern AT does not occur anywhere in the string. You see? The reason I put a T there, not C. For example, would it solve the problem if I put a C at the end? No, because in that case, AC also appears here as a prefix of another suffix, and it also appears here as a prefix of another suffix too. But putting a T there, I ensured that AT doesn't occur anywhere in this string. So I actually take a look at, do we have AT here? No. So putting T here is safe, because in that case, AT does not appear as a prefix of another suffix, and this solves the problem. But in general, when we're going to build suffix trees for DNA sequences, can you make sure AT doesn't occur here? Oh, actually, I have a problem, right? Okay, AT doesn't, I still have a problem. I didn't solve any problem at all. All right, you could actually, you should have argued with me. T here by itself is still a prefix of this suffix, right? So when we come to insert the last 11, so putting T here does not solve any problems actually. T, because that suffix T is a prefix of this suffix that starts with TGACAT. So in other words, T is also going to end up prematurely at the middle of, at some intermediate node. So the way we solve this is to put exactly. So that was just what I was going to say, Alper. So this is exactly, and that's the dollar symbol that is used. So you're spot on that we have on the examples. So we put a symbol that doesn't exist that's not in our alphabet. So we have a DNA alphabet, ACGT. We have a protein alphabet, 20 letters. If we put some letter that doesn't exist in the alphabet at the end, and let all of our suffixes end at that character, it means that they will always have a leaf node. In other words, it's basically also saying that I allow instead of empty string, I allow edge labels to have this character $. So when you have that final $T at the end, this is your string. It's going to appear like this, and you have this $ also appear as your final suffix here. But yeah, that will solve the problem by putting an arbitrary character at the end, which doesn't exist anywhere in my string. We'll make sure that no suffix is a prefix of another suffix, because having this non-existent character at the end, it means that this will never occur here anywhere in the middle of the string, because that's a non-existent character. So no suffix can be a prefix of another suffix. So this is how we solve it. And I just described the construction algorithm. In order to insert a particular suffix, as you can see, we spent, when we are inserting suffix I, we spent OI time, where yeah, exactly. We spent OI time because it contains I characters, or n minus I characters, right? Right. So it's actually 1 minus I. Or when we're inserting suffix I, we spent 1 minus I. So in other words, it's actually OI time. It's 1 minus I still, but if you just change your variables and make, when you're inserting the first suffix, so in other words, what I want to say is we actually spent this much time. So let me define it like this. If the length of suffix si is this length, we spent this much time for inserting a single suffix into the tree, because we look at its characters one by one while we're inserting it, and that's how much time we spent. And since we have n such suffixes, this construction algorithm therefore is quadratic. Okay, so the summation of I is equal to 1 to n, I will give you O n square. So this is an inefficient way of constructing the suffix tree. There are ways to construct suffix tree in linear time, but I'm not going to discuss them in this course. But here's how we can construct a suffix tree for any given character. Now, how can we search for a pattern, given an arbitrary pattern? For example, does GAT occur in this suffix? How are we going to find whether GAT occurs in this, not suffix, whether GAT occurs in this uh, entire string or not? If it occurs, it has to be a prefix of some suffix, right? So the algorithm of searching is very similar to insertion of a new suffix. We are trying to match, we will try to match the characters of our pattern one by one, starting at the root node. And if we can match all of the characters successfully on some path, it means that that pattern exists here. But if we get a mismatch in our path, if, for example, this T mismatches with the C, so we are unable to continue on this path to find that pattern, it means that pattern GAT does not exist in the string. So it's this simple, and I just mentioned general properties of suffix trees and how they're constructed and how a pattern is searched in a suffix tree. Okay, so I'm going to quickly go over some examples on Thursday, but this basically concludes our discussion on suffix trees. It's a very simple data structure, simple to describe and build, but their extensions are maybe complex. But we are going to just simply know this data structure. And we'll also see an extension named suffix arrays. Instead of having this tree as a dynamic data structure like this, building a suffix array in n log n time may also be preferable, because it has, in terms of space, it's really, although they are both asymptotically linear space, the constant factor in suffix arrays is very small. It's just an array of suffix indices. But we will not be able to conduct search in suffix arrays in linear time on the size of the pattern, but in logarithmic time. It's going to be still, therefore, very fast. Okay, so that's one extension we will talk about, suffix arrays, on Thursday. Okay, now I will stop recording, and we'll be happy to answer any questions you may have. And since this is our office hour that is continuing, I will stay here as long as you have questions.